Good morning, good afternoon, good evening, wherever you're dialing in from today. Excited to have you folks here. We're going to be talking about a really exciting topic again in the industry, especially in the retail industry, how to architect a modern retail global product catalog. And just for the quick introductions, my name is Amey Banarse. I lead the field solutions here, engineering team here at Yugabyte. Been here for about 6 years now, and really working with our customers to develop their solutions architecture. So end-to-end data pipelines, and then helping them modernize and sometimes build out new applications, which basically take all the benefits from a distributed SQL database. With me today, I have Don Bizzell, who is actually pretty well versed with retail industry when it comes to global product catalogs, given the fact that he has done this at least 3 times in his career before joining Gigabyte. So with that, Don, I'll have you just give a quick introduction for our audience today before we get to the sessions.
Well, I'm an old database guy. I've been doing databases since, I don't know, the 80s, and been working with major retailers around the world for over 30 years, and been with Yugabyte now for 2.5 years, been doing distributed databases for 6 years. I'm really excited about being here today.
Nice. Thanks, Don. I'm glad to host you here. So, folks, for today, what we're going to do is get into the nitty-gritty details of what is a global product catalog. And before that, just want to set the context of before getting to a use case with something like that, what exactly is a system of record? So, as per the definition here by some of the largest and celebrities in the industry, think of system of record as your global source of truth for any data that you serve to your end customers. Now, those end customers can be a consumer application. Let's say you're a bank and you're giving your checking account, savings accounts, your profile metadata information. So that's a system of record. Or it can be an automotive industry where all of your telematics data becomes a system of record because that's what basically stands for making a decision down for downstream application. But for today, we're going to be focusing on system of record mainly from a product catalog perspective. So this is how it looks. The system product catalog here talks about what all data sets in this example is basically it's holding a system of record in a way that if something changes, all the downstream applications get affected based on that. And they can be, as I mentioned, consumer facing, internal facing, your associate groups, like your workers in your factories and retail stores can consume these kind of information. A lot of the data sources here comes from various streams. They can come from your internal ERP portals, they can come from your merchants, they can come from your own products that you sell on in your retail store. So those are the data sets that we help aggregate, put it in a streaming solution, and then put it in a serving tier with Yugabyte, wherein that gets served as well. So those are the things internally we're going to take a look at. And if you look at the key database characteristics here, like usually for a system of record, given that it's a product catalog, you need accuracy of data as a number one thing. You don't want a customer to complain that, hey, I didn't buy this product, or you know what, I had bought this product, but I didn't get any rewards for that. So those kind of situations are the ones you want to avoid completely in a retail experience in general. Obviously, there are other things that we're going to take a look at in our session today, but mainly it comes down to scale. That is, your during holidays, Black Fridays, Thanksgiving, your cluster should be able to scale seamlessly without impacting your end customer. At the same time, if you have a natural disaster or a man-made disaster that hits your data centers or your solutions, you don't want to affect the customers at all. And if at all you have to do, the impact window should be minimal to a point where it's predictable and it doesn't put any toil on your operators. So those are the things which are top of mind when designing such a system of record solution, at least in the retail industry. Now, with that, as we mentioned, I have Don here who has actually built the system of record global product catalogs in his last three companies where he worked. So we're going to deep dive into how to build it with distributed SQL database, which is Yugabyte. And again, for this example, we chose one of the solutions that we have built over the last 4 years. But in general, Yugabyte has been pretty popular solution in the retail industry, given the fact that we do a lot of shopping carts, shopping wish list, global product catalogs, merchant categorization kind of use cases in general. But the theme that we
Wow.
see, recurring.
I mean, it's not like retail needs high speed, lots of scale, always
Hmm.
available, right? So that's why they come to us. This is a perfect fit.
Correct, correct. And folks, if you see during COVID and from COVID, the online shopping experience has grown 5 to 6x. Every retailer's topmost priority comes down to these four things: enhancing the experience of end user, increasing efficiency of delivering the product, as well as making sure the product is available, ready to go. So the whole supply chain efficiency becomes important. Building that loyalty with respect to trust, privacy, making sure it's always available so that you don't have bad experiences. And in a way, embrace more modernization, diving deep into cloud native stack. That becomes the foremost thing for the CIOs and senior architects thinking about the prioritization in this one. And in general, the use case that we're going to talk about today is mainly from a global retailer who serves this data to a worldwide audience. But for today's use case, we thought we'll focus mainly on the US market. That's where 80% of the traffic comes from. And in here, the main use case in front of us would be: how do you scale to handle peak holiday season? How do you make sure that your solution is resilient even if you lose a node or an availability zone or an entire cloud region without impacting any data loss kind of scenarios? And then few things around that, like you want the solution to be platform agnostic. Like today, I run in my data centers. As you know, most retailers have really good investment in their data centers, but they always like to try a cloud or two to make sure that they get that seamless end-to-end experience or an at edge experience at their stores as well with their customers. So, with that, just a recap before we deep dive into the technical details. This retailer specifically went through an amazing journey over the last 10 years. So, exactly 10 years ago, they were a very happy customer with the red box here with Oracle. The issue mainly was that they couldn't satisfy the end customer conditions when it came to resiliency of data. So, if you the other things are in there, that is scalability wasn't there, geo distribution wasn't there, but the main point was that the resiliency just wasn't possible with Oracle, Monolith, RDBMS. So what they did was they spent about a couple of years trying to break the shards of data manually and still doing app level sharding with Oracle. So think of it as simplest case: if you have A to Z letters and all the products aligned on that, every single shard of the database, let's say I have 26 shards, every single shard of the database will have products starting with letter A to letter Z, kind of a thing. Now, the problem in this is if one of the shard goes down, the operator has to quickly go figure out how to get the other part of that replica back up. That takes downtime. That takes a lot of manual effort. And at times, you have to keep the solutions on 24/7. So even the people behind them are on 24/7, which is not a good, healthy thing for the operator teams.
Yeah,
Obviously,
imagine how
yeah,
much money somebody like Amazon would lose if they couldn't take orders for 10 minutes. I mean, you're
exactly.
talking millions of dollars here.
Exactly. So geo distribution was complex in this scenario as well. And the bigger part was they just couldn't figure out how to get the replication done in a seamless way, on a strongly consistent way across different regions in the country. With the advent of NoSQL databases, so let's say circa 2016, 2017, they started to invest more on NoSQL by flattening out their data models. But the challenge was they couldn't get the asset compliance that was available in the earlier solutions. So for which they basically build the applications in a way that they can handle transactions in the application, which put a lot more overhead on the app developers. And that solution worked for the scale part of it with NoSQL, but did not work to meet the asset guarantees, the transactional guarantees that was absolutely required for their applications as well.
And we've
So,
all experienced that, right? You put something
yeah,
in your shopping cart, you go to check out, and it says, "Oh, it's not available. We're out of inventory or whatever." What is the first thing you do is you go to a different website and buy it from them. So they were
correct,
losing business because they just couldn't keep things in sync or have strong consistency.
correct. So to set the stage for the technical details here, we are saying that the workload basically is high throughput, low latency with 90% reads and 10% writes, which is usually the basic characteristics of a ledger or a catalog use case in general across the industries. Consistency, as I mentioned, asset transactions are a must. You want to ensure that if something goes wrong, you're able to roll back the transaction correctly. You should never leave the transaction in a situation where you never know what the real state of the data was. The third and the fourth thing are extremely important, as you can imagine. Millions of customers shopping every day in the United States. So performance trumps everything when it comes to end customer solution. So we wanted P99 latencies to be between 3 to 5 milliseconds, writes to be 75 milliseconds. And we'll get to the part why we're saying 75 milliseconds there. And the last one is that in general, across the industry, catalogs get refreshed midnight to, let's say, 4 or 5 a.m. So most of the catalog almost always gets refreshed. And then there are like delta changes about 5 to 10% during the day. But you want to build a pipeline in a way that the entire catalog gets refreshed overnight. That means your bulk loading data performance has to be really, really solid during that time. So with that, Don, I'll hand it over to you. Walk us through how we build this solution.
Sure. Well, the first thing we want to do is we want to be separate the data geographically. So if one geo has a problem, the other geos can pick up, and you'll never even notice. This actually happened to this retailer where they have their primary applications and all their connections in the central region, and an ice storm hit, and that central region was down for 4 days. They didn't even notice that Yugabyte took a small hiccup of a few seconds while it switched to the other regions and got everything going. Didn't miss a query, because their Oracle systems were a mess at that point. They had to go scramble to get that done. But their catalogs, their websites, everything stayed up because the Yugabyte stayed up. And one of the reasons they can do this with the geographic distribution is they keep all of the leaders and all of what we call our preferred leaders in one region, so they get that high performance through the one region, and it propagates out to the other regions appropriately. And then using cluster aware drivers and topology aware and so forth, it makes everything, the applications don't have to know how the database is architected. The applications just see a database. It's a simple Postgres or Cassandra database, and they can just connect to it and work with it as they were right there next to them. So that makes development and maintenance very simple.
Right. And Don, I can quickly touch on the last point. So folks, imagine this solution being developed in a cloud native era where you want to make sure that you do as much as async reactive microservices as possible. So in this case, we were fortunate enough that we use Akka framework to make sure that all the microservices don't always hold on to the connections. They will, whenever they need the connections with the database, they can go fetch it directly. And that's the best part. Yugabyte, being born in a cloud native era, was fully compatible with this reactive microservice solution. So think of it as hundreds and thousands of smaller microservices doing stateless microservices in general, and then connecting to Yugabyte whenever required to get the state of the data itself. So pretty scalable communication pattern.
But another advantage of having your data distributed geographically like this is it's not very far from any place in the country to one of these servers. So you get very low latency getting from a store in Oregon to the West set of servers, for example. Well, that's great. You're running a website, so everything can be kind of centralized and working. But now I'm going to add, I don't know, 5,000 stores to this. I start hitting the product, because product really is the center. We'll talk about this in a little bit. Product's the center of, supply chain and distribution and marketing and point of sale, and all these things all come together at product. So I could have thousands of applications hitting this database, and now I'm adding the stores and users on their cell phones walking around the stores, and suddenly I've got a lot of connectivity going on in parallel, lots and lots of reads. So one of the ways to handle that is by adding read replicas to each region. Now each region has a read-only version that stays up to date, but a read-only version of all of the data in each region, so that you get very low latency responses to read requests. And this is a 98% read system, so that makes very good sense. The read replicas also add more servers to each region, so you now have more connectivity, more concurrent connections that can happen in each region. So we're exploding that up, and that can explode up during the Christmas and holiday seasons, and then come back down in the winter. So it's very simple to manage this and scale it in and out as needed. And you might be thinking, okay, I might have the occasional, I'm working on my app, I'm standing in a store, and I suddenly decide to update my profile, and I need to send a write through the system. Well, I'm connected to a read replica. The read replica takes the write, says, oh, this is a write. Let's send it to the correct place, sends it to the central cluster, to the correct location for the reader of that write, and it gets processed as normal. So the read replicas will take writes, they just pass them through to the main cluster.
Right. So Don, this is great. Thanks for sharing the topology. Now let's get into the nitty-gritty details of how you folks have designed this global product catalog with a distributed SQL solution.
So first of all, this is a 20-minute session, so I didn't go into all of the details of product catalog, right? I wanted to give you a good representation here, and some of the highlights and some of the real optimizations that we've put in. If originally this product catalog was in a NoSQL language, and it was fully denormalized, which meant for every SKU, every product, there was a row, and you've got thousands of, and a SKU is a store and product combination. So a can of green beans in Louisville, Texas is a very specific SKU. It's separate from the same can of green beans in New York, for example.
Right.
So you can see they very rapidly got to having billions of rows in one basic table to manage, and it got to be untenable for even for a NoSQL type solution. So we're breaking these into groups, right? We'll keep the SKUs separate from the products. One product might have 5,000 SKUs, for example. We'll keep the related products for the website separate. We'll keep the suppliers and all the supply chain information separate, and the marketing and the discounts and so forth. We'll keep all of that separate. And so we can join these very quickly, but not with joins, but with primary key lookups. And that way we can get that NoSQL speed of being able to work with these tables and products, but still have the flexibility. There are other tables in this system that you would do joins with, right? Or have other indexes and so forth with. So that makes it much, gives you the kind of the best of both, right?
Correct.
Cool.
So, Don, do you want to tell our audience about the JSON-B data type? That was a pretty unique thing that you and the team worked on.
Right.
To convert few of the data types into JSON-B and essentially keep the app developers also happy. So why don't you tell our audience about that?
Yeah. So in the relational world, when you had multiple attributes, right, you had to have kind of a separate table structure for each attribute. So you had a kind of a table structure by department, and even that was kind of fudged because even within departments, attributes can change. And so to fix that, we put in a JSON field for attributes. And this is a completely, so you get your structured data so everything works and it's easy to program and it's easy to maintain over time. And then you have your unstructured portion with the attributes as a JSON field. And in this case, we're storing it as a JSON-B to make it more compact and faster to look up and so forth. And you can see the blue boxes here on the screen represent what would be JSON attributes. But product attributes is the perfect example, right? If I'm keeping the attributes of a television, how many HDMI ports, what's its diagonal size, what's its pixel density, those kinds of things for a TV. Well, none of that would apply to, say, a shoe, right? Or an orange, which produce might have a shelf life date and some other things you want to keep track of. So these attributes can be very flexible within a rigid structure for keeping your applications going. And again, this becomes the kind of the core of your whole system.
Right. So I think,
The supply chain, for example, when you need to reorder products, you can get to the supplier of that product very quickly.
right,
But maybe once a month, you want to go and see all the products that that supplier supplies and what what your margin is on those products. Get a margin report for the products from that supplier. But you only do that like once a month, right? So that's a perfect example of getting at data a different way and being able to use a secondary index to look things up in a different way.
right. So Don, one thing I'll highlight here for our audience is the performance benefits of using JSON-B, right? So before that, I mean, when they were using Cassandra, Cassandra really did not store JSON-B as is natively. It would convert it to string literals. So it put a lot of onus on the app developers to reconstruct the JSON-B and then render it on the web pages and microservices and things like that. With Yugabyte, they were actually able to tap into JSON-B, go through the different facets, look up secondary indexes, as you mentioned, in one single query. And that gave a huge performance boost and actually reduced a lot of round trip times between the app layer and the database layer for most part. So the real output of that is when the customers are now scrolling through the website or browsing it through their mobile phones, it's an extremely fast user experience. And that just attributes the way creative data modeling was done during this phase of the project.
And
So,
Yugabyte allows you to use all the operators to really dig in and only get the pieces of the JSON that you need, which is
correct.
very important. And by the way, we also allow that in our CQL, our Cassandra version of the database as well. So you get it, you get the best, you get it in both scenarios.
Right. So Don, let's
Okay,
do this.
let's look quickly at some of these scenarios. For example, you're looking at a SKU. From the SKU, you get the product ID. You know, a few milliseconds later, you've got all of the product information. A few milliseconds later, you can have all of the discounts for that SKU, right? And even though you need to do is it within this range? Is today's date in the valid range for that coupon? Is it in the right region? Is this coupon valid in this region? And you can look all that up in just a very few milliseconds because you've got a primary key lookup into the main table to begin with. And then the next one here is to be able to find the related products. Right, you're on the website, you want to see what's related, you want to see what the latest things bought with this product are. Again, we're going to keep those in a JSON, but instead of an unstructured JSON, this will be more of an array of product IDs, but an array that we don't know the size of, right? It could be 3 items, it could be 30 items, who knows? But we want to be able to get that as an array very quickly. And again, doing that primary key lookup gives you that, and we're not having to do long joins or anything. We get them very, very rapidly. And let's go on to the next screen.
Right. And folks, just to mention our previous slide, we were able to meet the SLA of the milliseconds given by the customer architect by doing these set of optimizations in our queries itself. So yeah, go ahead, Don. Share more knowledge on the queries.
Here's an example of actually using the JSON-B. I wanted to give some example of you getting text out of the JSON-B. So you're at the register, you're scanning an item, and you need to know what the little short name of that item is that's going to be printed on the register tape, right? It's like 12 characters. We've seen that. You get your register tape and it says blah, 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 right? But that's the short name for the item you bought. Again, a primary key lookup, so it's a 2 or 3 millisecond kind of lookup, and boom, you've got that. You can get those. You can get the price, the short name, and all of those things in less than 1/10 of a second. So faster than you can scan the things across the scanner. Right. You're getting this information out of the database, and that's why the SLAs are so small on these things. Right. And then the last one here, get the current list of suppliers for that product. So we've talked about this is for this region, right? I want to see who's supplying this, piece. It could be a vegetable, it could be a shoe, it could be whatever, a piece of clothing. I need to know who that supplier is, and what their terms are, so I can reorder from them. So again, product catalog sits at the heart of all of these different systems, and having a fast, flexible catalog is really important.
Right. So now, Don, let's do this. We spoke about the goodness of JSON-B and how it helped us with performance and also creative data modeling, thanks to you and the team. Let's spend about 30 seconds on secondary indexes with JSON-B, because I think that was a game changer for us, given the fact that our secondary indexes are strongly consistent and transactional. It actually allowed the application developers on this customer side to save about, on an average, 4 round trips when it came to reading and writing data. So let's give some more insight on that.
Well, and the key here is that we have the full access to all the different types of indexes. So your primary, again, we talked about our primary access patterns are going to be through the primary key, basically the way the table is sorted. So it's very fast. But now I have these secondary access patterns for all of these tables, right? There's going to be other ways I need to look at, maintain, and work with or report on these tables. And that's where secondary indexes really pays a dividend.
Right.
You can do just a plain secondary index, or you can do um, and a gen index where you're searching through products for, say, what their attributes are. You can do covering indexes, which include some actual data. Since we treat each index as a table, it's easy to add a couple of columns to that table. And now an entire query can be solved with just the index. We can look things up in the index and not have to go back to the main table to get the data. So that goes very quickly. And even partial indexes. I just want to see the products that are currently active. Some products are in the system, but they're not active for a while before they drop out. You could have active. You can do partial indexes as well, and this gives you a lot of flexibility to solve all the other things around your primary use cases.
Right. So for the developers and the architects in the audience here today, these two will help you boost the performance so much with your system design with Yugabyte. More importantly, it will make your app code really easy. So that way you can scale more without having to put much more overhead on your app developers or backend database system. So definitely read it up. We have a fantastic documentation on these two features, as I would call it, in our Yugabyte official docs. So with that, Don, thank you again for sharing everything. Folks, what we wanted to do is we want to give you a snapshot of the work that we have done with this specific use case over the last 4 years. And as I had mentioned before, we are pretty predominant in the retail industry. We worked with likes of Kroger, Tokopedia, and a few other large retailers in the world, where they serve millions and millions of products in general to the end customers. So real quick, the performance snapshot across 3 different vectors, as I've written up here. The first thing, when it came to cloud native microservices or reactive microservices, the our platform, like Yugabyte platform in general, was able to support 100 plus million products and billions of product mappings throughout the last 4 years. And the way data got into Yugabyte was through combination of Spark and Kafka. So as we had mentioned, data comes from various different sources. It can be a merchant, it can be an in-house warehouse, and then it comes into Yugabyte after cleansing, so that it's system of record in the serving tier. But downstream applications can also consume this data through various different aspects, read replicas being one of them, and then it goes to downstream analytical platforms if needed. The other thing was that the entire application architecture is extremely scalable. So during a normal day, let's say if it runs at 1x, during holidays, it can run on 5x without any manual overhead required from the operators itself. Now let's talk about scale, a great segue. On a normal day, we do about 250K transactions a second. And that one transaction for a read actually goes and touches 5 or 6 different tables internally. So the ops per second typically is about 1.25 million ops per second. And in terms of writes, as we have listed here, it's a multi-region solution. So we have optimized in a way based on the traffic patterns. We put all the leaders in the central region to optimize for performance based on that. And without any issues, our CPU usage was in line, not more than 60% throughout the experience. And the last part, the operational efficiency, is the most important one here. Routinely, we help them do chaos monkey testing. So we would take out a node or an AC without any issues, without any impact to the end customer. But as Don had mentioned, there was one big natural disaster which took out the entire cloud region in the central US without having any data loss or an impact, or and guaranteeing RTO of zero to the end customer, or RPO of zero to the end customer. So that was something which is substantial, something that couldn't be done with the existing solutions that they had in place. Don, anything else you'd like to add? We are on the last
Just
minute.
that this is a very efficient system. They're doing this with just a few 12 nodes in each region. Now they've added several read replicas in each region as well now. But this kind of performance from 12 nodes in each region is just phenomenal. So it really makes it low cost of ownership as well.
Right. So, folks, just to wrap up, what we're going to do is, again, Don, thank you for your time today and sharing all the best practices. We are going to follow up with a technical blog on all these details so all our audience can go and read it. And then it'll be followed by a little bit technical depth webinar as well. Because, as Don said, 20 minutes doesn't do justice for this topic. So, we're going to follow up with a lot more technical details in query optimization and data modeling as well. But with that, please start us on GitHub and join our Slack channel. We have an amazing community of users who do creative solutioning every day, and our team's there to help you all the time. Thank you again for your time today, and look forward to seeing you next week. Thank you.
Take care, everybody.